Well, hello, folks. Again, I just found out I made it dumb, and we were not broadcasting live on the show, so this one is kind of messed up. So we're showing a comet, and I will come back and take full responsibility for the fact that the software was showing me we were live, and so I assumed we were, and it turns out we were not. So I apologize for that, and will reiterate that this is the Cosmic Pie. Myself, I am Robert Moore. I'm the lab supervisor here at the University of North Dakota for the Department of Physics and Astrophysics. With me is this week in place of Professor Barkhouse, who is out for the day, is Professor Dean Smith, one of our professors here at the other professors here in the department. And we've actually recorded quite a bit of the show already, 10 minutes. So we don't have the usual opening or anything else. I'm sorry. I pulled a dumb. I was lied to by the equipment, and, so we're kind of messed up. So we're going to kind of, I guess, go back over a little bit of the things. So we started out by talking about... That was the wrong button. I'm really doing well today, folks. How are you? So we started talking about these headlines of these green comets because recently we've all heard, rare green comet. We've got another one coming, in fact, rare green comet. And this is a list of headlines from as far back as 2017?
Yeah, so this was a screenshot of a Google search, and in Google you can limit the dates. And so I just told it, well, show me search results from before 2023, and we get a bunch of headlines of a green comet, and these are other comets. And so I thought I'd bring this up because there were a lot of headlines again about a green comet, and I know a lot of people got the impression that there was something rare about this. And people are calling it the green comet, like
there's only one.
Yeah, there's only one green comet. No, most comets do have green on them, and these are a bunch of past headlines, and headlines about green comets in the past. And so I did bring some pictures that I took of comets over the years.
So let's look at this one first again.
Yeah, so this is a picture I took in 2015. And this is what I remember taking these pictures and thinking, I have pictures of green comets. Isn't that weird? And so, right. So this was in January, and we're in North Dakota. I normally don't go. In fact, I have some pictures of this through a window because I didn't want to go outside. But then it passed by. It's January.
It's January in North Dakota. Why would you not want to go outside?
So I did go out because it was next to this star cluster. And so in the upper left is the Pleiades star cluster. And to the lower right is this green fuzzball. And most comets look like green fuzzballs. And a lot of these you don't see a tail. And they look kind of like this. This is actually a lot of the comets that I've seen over the years are these little green fuzzballs. So the green is actually pretty common. Go to the next one here.
Okay. And so yet another green fuzzball right next to the Pleiades.
Yeah.
So if you look in the lower mid-central, you'll again see the Pleiades cluster. And right next to it to the left is the green fuzzball of Comet
Virtanen, I think this one is. So this is in 2018. This was in, I believe, December. So bad luck with winter comets up here. But again, it was by the Pleiades, so I went out again. And
you must like the Pleiades.
Two things next to each other makes for a nice picture. Yeah. So this is the Pleiades star cluster, little green fuzzball again. This one did get a red giant star in the upper left is Aldebaran, which is a red giant. So it's kind of a neat thing as well.
So what is causing this green color? We discussed this already on the recording, but I figure we'll bring it up again, if nothing else, but because we weren't live. So what causes the green color?
Yeah, so this shows up at the very front of the comet, right around the actual solid part of the comet called the coma. And this is a carbon molecule. And so the carbon molecule will give off this green color. And again, it's just right around the front. And most comets, we don't see a lot, we don't necessarily see a tail. And so, yeah, green fuzzball is actually really common for comets.
Like you've mentioned, we've seen pictures of two different comets now that showed no tail. So now we'll fix that, and we'll look at this comet.
And this was the green comet, right? So this is the one that was just around over the last couple months that made a lot of headlines. And this one does show a bit of a tail. There's other pictures that show much nicer tails. This is the picture that I got. And notice that it's the front of the comet. That's the green fuzzball. This is the coma. But the tail isn't green. And so I think a lot of people don't associate green with comets because we think of the tail, right? And
Right.
a lot of the nicest pictures of comets are showing these big, long tails.
The bearded star thing. Yeah.
So
I also will like pointing out again that this image is also neat to me because if you look up in the upper left corner, you'll see this nice little fuzzy streak. Well, that's actually an edge-on galaxy, probably a spiral. And that's what galaxies look like in a lot of these frames. And you'll be shooting one target and you'll accidentally get just a screen full of galaxies if you look around, because I can see several others that are in there as well.
yeah.
But that's what galaxies look like. They're just fuzzy little blobs or fuzzy little streaks where you have pinpoint bright dots for the stars. So, just thought I'd mention that and point that out before we go on to our next comet.
And that was just a camera with a lens on it.
Okay.
So that wasn't even a telescope
That
picture.
wasn't a telescope.
So you can take pictures of galaxies with just a camera. Now that was on a tripod tracking, so that so it was a long exposure. So, but yeah, you can get galaxies without a telescope.
It still couldn't have been too long an exposure because your comet isn't streaked, but nor are your stars.
Right. So I was tracking on the stars, but it wasn't too long. I think this was about a minute. So the comet didn't move enough to notice.
Right. And I'm pointing that out because I notice on this one, if you'll notice, the stars are kind of streaked.
Right. This is a telescope image.
Mm-hmm.
So this is zoomed in. This is the comet Neowise from 2020. And so this is a well-known, well, hopefully well-known comet. This was naked eye, and you could go out and look at this and see it. And most people, a lot of the pictures you saw didn't show the green here. This is a telescope picture zoomed in on the front, the coma there, and you do see this greenish color again. And then there is, some of the tail, but that coma is really bright and kind of overpowers the rest of it.
Yeah, I mean, you it's like anything else. You see what you're looking for.
Right.
So if you want to see the tail, you pretty much have to overexpose the coma.
Yeah.
But if you want to see the coma, you pretty much don't see the tail.
And even in this one, there is overexposed in the center. It is white there.
It's white there.
So this was actually overexposed.
Yep. And again, I'll point out that if you look at the bright white dots that are scattered throughout, those are stars, and you'll see they're streaked, which is what happens when you track a closer body like a comet or a planet for any length of time. The stars will streak because they're moving at different rates. The stars are practically stationary. So, just pointing out some things about the astro images. And so here's another one of Neowise.
Yeah, this is the same comet. Now that previous one was in a telescope. This is a camera lens. And it's about a factor of 10. So the telescope is zoomed in about 10 times closer just on the very front of the comet. This is a camera lens, so zoomed out, and now we see the tails. And notice you don't notice the green. You might see a little green fringe on the very front of the comet, but this is one where you see the tails. This is what people think of when they think of a comet, is these big tails coming off, and you don't notice the green. So I think that's part of why people don't associate green with the comets.
Right.
It's the fainter comets usually that without much of a tail. And so there are two tails, and one's obviously a lot brighter, and they're different colors. So this white tail, the brighter one, that's a dust tail. And so this is dust that came off the comet. It is reflecting sunlight at us. Mm-hmm. And so we're just seeing reflected sunlight. Usually will look white, maybe yellow, It'll depend on how high it is in the sky. Comets are lower down, they're going to look more yellow on that dust tail.
Why is that?
Well, the same reason the sky is blue. The atmosphere scatters the blue light, and if you take white light and you remove the blue, you got yellow
You
left
got
over.
yellow light.
So
And so why is that other tail blue?
right, so that one is actually glowing. So the dust tail is reflecting sunlight. The blue tail is called the ion tail. So it's ions, it's a plasma, and the gases in the ion tail are actually emitting their own light. So it's glowing blue, and so it's usually much fainter, much more difficult to see. This comet, you could go out and see the dust tail with your eye. I couldn't see the ion tail with my eye. That was a lot fainter. And it'll be hard to point this out, but do you see the galaxy in this one? There's a galaxy in it.
Oh, there's a galaxy.
Right next to the ion tail.
Yes, it is. Right above it.
Yeah.
Right there.
There's a little galaxy there too. Complete accident. I did not go out because there was a galaxy there.
Nearby.
So it just happened to be there.
You'd be hard pressed to find out which galaxy that is.
Yeah, I did identify it at the time.
Oh, you did? Okay.
Yeah, because you can look in software where the comet is and see what galaxy. And so I did. I don't remember what it is now, but I did identify it at the time. So, yeah. So sometimes you just happen to get a little galaxy in your pictures.
Yeah, you get a 2-for-1. So that's our look at comets and everything, and the fact that people trying to act like these green comets are a special and unusual thing. I hope we've kind of dispelled that. Not that it should take any of the wonder out of going out and looking at a comet.
Oh yeah.
Unless you're in North Dakota in January, in which case they're giving you weather forecasts of how likely you are to die out in it. I recommend that you take every opportunity to go out and look for bright comets. Take a pair of binoculars, or some of them are bright enough that you can see with just your eye. But in the end, the thing is you don't need a telescope to see a lot of this stuff. A set of binoculars or something will do just nice. I've watched the moons go around Jupiter, the 4 bright Galilean satellites, with just a pair of binoculars. And so I'm kind of glad we brought up this topic, because a lot of people think you've got to go spend thousands and thousands of dollars on expensive equipment. And it's like, no, you can appreciate this stuff with a cheap pair of binoculars.
Oh yeah, quite a bit. Yeah, common pair of binoculars that you might have sitting around. You might use them for something else.
Mm-hmm.
You can see, quite a bit in the sky with it.
So, break them out. Go out and look. How do I know where to look? How do I know how to find these things? That takes a little more trial and error, but at the same time, it's worth doing. And most of these magazines like Astronomy and so forth make some really good sky maps that you can help you find where things are. So I'm kind of glad we brought that up. And in fact, let's segue into that. And let's look at what's up in the winter sky right now.
So I am the faculty advisor of the astronomy club, and one of the things we do is we go out and we go outside and look at things, and we'll take telescopes out, and so and it can be a good way to also introduce some interesting objects. So two of those comet pictures show the Pleiades star cluster. That's out right now, and you can see it in binoculars. And so I wanted to kind of show how to find that. So this shows the sky tonight from Grand Forks. Now, if you're in a different location, it might be a little bit different. I think I put this at 8 p.m. And so at 8 p.m. you look southwest.
Yep,
looks
8
like
p.m.
that. Okay, good. So 8 p.m. look southwest, and you should see Orion, the constellation Orion. If you're trying to learn constellations, maybe you don't know the sky at all. A good first one is Orion, because it's bright, it's easy to find.
The 3 belt stars give it away every
Right. Look for those 3 belt stars. They're right in the middle of the picture here, horizontal. You find that, and then you can work your way out. And so the Orion constellation, so Orion the Hunter, there's a couple bright stars that are labeled here. The upper left is Betelgeuse. That is a red giant. And people always ask me how far away things are, and I never know, so I labeled this. So I can just tell you, Betelgeuse is roughly 500 light years away. And then on the lower right is a blue giant star, Rigel. That's 850 light years away. And so the temperature has to do with the color. And so just from the color, I know that Rigel is a lot hotter than Betelgeuse. Some other interesting objects here that you can find using the belt. Take the Orion's belt and follow the line to the lower left. It gets you to the star Sirius. Sirius is the brightest star in the sky. If you see a star brighter than Sirius, it's probably a planet.
Probably.
If it's moving, it's probably the space station. But
or an airplane or,
yeah,
or something like that.
So now Sirius is bright because it's close. It's only 8.6 light years away.
Only.
As far as stars go, and if you look at these other ones, that's fairly nearby, right? That's the closest one that I have labeled here. It's not the closest star, but it's one of the closest. Okay. So it's bright. It is a little brighter than the sun. It's a little hotter than the sun, a little bigger. But mainly it's bright because it's close. So if we go up the other direction, take those same belt stars and go up the other way, we get to Aldebaran. Aldebaran is another red giant, but is a lot closer, 67 light years away. And then you go a little bit past that, and you might see with your eye a fuzzy patch in the sky. That's the Pleiades star cluster. That's a star cluster that showed up.
I will mention that a lot of people misidentify it as the Little Dipper.
Yeah.
Because it is dipper shaped. The 6 stars in it that you can usually see naked eye have a dipper shape to them. But the problem is the Little Dipper, one of the stars in it is Polaris, the North Star. And you're not looking to the north when you're seeing the Pleiades.
Yeah, this is definitely not that.
So this is definitely not the Little Dipper because it's not in the northern part of the sky. So keep that in mind. But it's easy to identify the Pleiades because of that, because it is faint and fuzzy looking, and it does have a little dipperish shape to it.
Yeah, you can call it the very Little Dipper.
The microscopic dipper.
Yeah.
Because the Little Dipper, folks, is only little, as I put it, in comparison to the Big Dipper.
Right.
It's actually a pretty big section of the sky, the Little Dipper is. But it's small compared to the big one. So, anyway.
Yeah, and what this star cluster looks like will depend a lot on the light pollution in your area. Mm-hmm. So a lot of people will just see this as a fuzzy patch in the sky. Right. If I go out into a dark sky, I can tell that it is made up of stars. And then definitely, even if you're in, at least, Grand Forks-sized town, if you take any pair of binoculars, and this is maybe one of the 2 best binocular objects, you take any pair of binoculars, you look at this, and you will see that little dipper shape of stars in that star cluster. And so, and this is a little over 400 light years away, so fairly distant. So notice there's a big range in distances of these. Now, I forgot the one big thing here. Below the belt, there's a fuzzy patch. You might see this with your eye. You definitely see it in a pair of binoculars. That's the Orion Nebula. It's actually the furthest thing I have labeled on here. It's over 1,000 light years away. This is it's a nebula, so it's a giant gas cloud. And this is one of the gas clouds where stars are forming. And so this is a star formation region. This is in the northern hemisphere. One of the nicest things you can look at in a telescope. So if you have a telescope, this is a good first target to try and get.
Yeah, if you have a telescope, this is a great target to try to find. If you're getting into astrophotography, you'll take hundreds, thousands of images of this nebula. Trust me, because it's one of the easiest ones to take. You can play around with it and see how the adjustments work, because there's a lot of faint material around it, but as we'll discuss and see in a minute. But there's also a lot of bright stuff. So you got to kind of learn your controls and for your exposure and all of that in trying to shoot that nebula. And so it's an easy target to find. It's an easy one to shoot, but it's also tricky. And so it'll test your skills.
Yeah. Did you want to show the whole picture of it?
Okay, we'll go ahead and jump to that one.
This is not what it will look like.
It will not look like this to your naked eye. If you put your eye to an eyepiece and a telescope even, you won't see this much detail, and it will all be green.
Yeah. So, yeah, that's an interesting thing. In pictures of nebula, most nebula will look red in pictures. This is one of the few nebula where I see color. Most nebula I see is gray. This one's bright enough, I will see this as kind of green. And that's mainly because your eye is much more sensitive to green than it is to red. And so the colors are coming. Again, this is like the ion tail. The gases are glowing here. Most of the color you're seeing is from the red is from hydrogen. If you look at it visually, you're probably seeing green light from oxygen.
From oxygen, right.
And your eye is more sensitive to that. So, Robert mentioned how challenging this is. When I take pictures of this, if I try and get all that nebulosity, usually I overexpose that white region in there, and it's just overexposed. And so it's a challenge to get the faint and the bright. Yeah.
Right. Most people do it, in fact, by shooting the center and then combining that later with long exposures where they crop out the center and replace it with their shorter exposures, and they manage the trick that way. So, you hear a lot of times, oh, these are all CGI'd image. No, they're processed image, but they're not CGI. They're not created whole cloth. They are pictures. But sometimes we can play with a picture to bring out details that we normally would not be visible when you use those camera settings.
Right, and so
you can use a little processing magic.
So yeah, a lot of these pictures, they don't look like what you're going to see, and they're off a little bit from reality, mainly in the brightness levels, because that middle region is much brighter than the outer regions. But to show everything, kind of have to flatten the
bright and bring out the dim. Yeah.
Right.
You just have to play with it to do it. So that's the Orion Nebula, and I like pointing out that the reason most nebulae are red, by the way, if they're being heated up, and in this case, this nebula is a star-forming region, so there's a lot of hot young stars in it. So the gas is being heated, and it's therefore glowing. And the reason it glows red is we know hydrogen has a very bright red line. It's even got a name, the hydrogen alpha line, and it's red. And so most of these nebula that have young stars in them are being heated up and made to glow. And because most of the universe is hydrogen, you see the hydrogen, you see the red. But your eye, so when you're looking through an eyepiece at this, it looks green because of the oxygen present, which tends to glow green, is because your eye is actually about 1,000 times more sensitive to green light than it is to red light. So a red source has to be 1,000 times brighter for you to see the red on an equal footing with green. So there's the explanation there. It's a trick of our biology. And
cameras, they have no problem. In fact, digital cameras are usually really sensitive on the red.
On the red side.
So, so we tend to see a lot of the red in pictures.
Yep. So we were talking about Betelgeuse, the bright red star in Orion. So this is it. It's up here. It's got little crosshairs sticking out to it. I'm trying to point to it, but it's in the upper left of the stick figure of the constellation. It's at the upper left. And like I said, it's got these 4 little crosshairs around it as well as the 4 diffraction spikes. And when you look at it through a telescope, it is distinctly red. And it will even be fuzzy because it's close enough and large enough that we can actually, you're not quite seeing it, but you're seeing almost that it's an extended object.
So this is one of the few stars that we have a direct image of. This is a Hubble Space Telescope image of Betelgeuse. So most stars, even Hubble looks at them, they're still dots.
They're still dots.
We can't resolve them, and so we can obviously see them. And some people do get that mixed up, thinking, how can we see something we can't resolve? But you can see the light from the stars, but we can't resolve it, so we don't see any detail on the surface. But here we actually have an image, and so we can directly get a size of it. And this is huge. This star, if you put it where the sun is, the Earth would be inside it. And so Mars would be inside it.
Jupiter would be inside it.
Yeah, so Jupiter would be inside it. So this is a huge star.
I will point out that this is also, it's a dying star, so this is one of the stars we're looking to go supernova in the near future, astronomically speaking.
Yeah, so this will explode at some point. It will be amazing when it happens.
Some of us go out every night and go, blow up already.
So, but we don't know. Yeah, we don't know when. It could be tomorrow. It could be in 10,000 years.
Right.
So
it won't be much more than 10,000 years, though.
we do
that's
think
how
it's getting to the end.
close it's to its end of its life. So then we have some pictures using a different type of telescope, a different technique, using the Chara array, which is redundant because the A in Chara the last A stands for array, so it's kind of like saying ATM machine, but most people still do it.
So, and these aren't any of the stars in there. These are just two. And I thought I'd mention, because a lot of people wonder, how do we know how big these stars are? We talk about them being giants. Well, there's a few ways, but one way, a few of them, we can image them with Hubble. I don't know if James Webb is going to try and image.
I don't think so. I don't think James Webb is designed to look necessarily at stars other than to then filter out, correct out their lights to see if you can see a planet.
The exoplanets,
there. Yeah.
So, but this uses a different method, uses interferometry. So it uses multiple telescopes spread apart. And you might have heard this with radio telescopes. This is common with radio telescopes to get high resolution images. And so now this isn't a direct image. Like it says on here, it's a reconstruction of data, but we are able to construct images of stars by using multiple visible light telescopes. And so this isn't a radio image, this is from visible light telescopes.
Yep. And I don't know much more about interferometry, which is what the technique used here is. But it's bottom line, it's using the interference nature of light. And most of the time it's done strictly in what we call Fourier space, phase space. And it's looking at how the light is interfering with itself. But if we have 3 or more telescopes at distances from each other and we combine their light from all 3, we can get images like this. So that's why it's called a reconstruction, because they've taken, with 3 telescopes, we can take that phase space information and convolve it or deconvolve it back into real space information, and that means it's an image. So, these, if we got closer, are what these stars look like. So they have bright hot spots and cold dim spots on them. They have oblong shapes like the one on the left, Rasselhog, because they're spinning, rotating quickly. But, this is one of the better techniques we know for just how big stars really are.
Right. Yeah, and there's more pictures, and I recommend looking at Google the Chara array, and there's other pictures, and it's kind of neat that some of these stars do have shapes. Some of them are really elongated because they're spinning so fast.
Spinning so fast. The bright one in Leo was one that they did that was Altair is football shaped. Because it's a fast rotator, and Regulus. That's the name of the star. Regulus is football shaped because it's a fast rotator. These we do have images of stars and what they look like using Chara and other interferometry based telescopes. So,
If you go back to winter sky, I want to mention one more
okay.
thing on there.
So back to this slide.
So Betelgeuse was a supergiant. It's a red supergiant. And there is another red giant in here, that Aldebaran. And I kind of want to point out they are roughly the same brightness. They're about the same magnitude. They're both about the same temperature. They're both red giants. But notice the difference in distances.
Right.
Betelgeuse is much further away. So how is Betelgeuse at the same temperature appear to be the same brightness as Aldebaran?
It's that much larger.
It's much, much larger. And so we're able to this is one way we're able to figure out size. The brightness of a star depends on temperature, size, and distance away from us.
And I guess that would be a good topic for another show on, when we're going over some of these basic techniques and ways that we know information, is how do we know how far away stars are?
Right.
Because that's a big question, a question I've been asked many times. And despite what a lot of people think, because they hear about redshift, we don't use redshift.
Not for stars.
Stars are close enough. We've got other techniques that allow us to determine how close or how far away they are. Redshifts is pretty much just galaxies. And that's not the only technique we have for galaxies. So we really probably should do a show
distance
sometime
ladder
on the distance ladder.
Yeah, that could take a good chunk of time.
See, we even have a name for it. We call it the distance ladder. So, go ahead.
I always got more things to say.
Absolutely.
But Aldebaran, that red giant, that's a little more massive than the sun. And so that's obviously much smaller, so we're able to see it from only 67 light years away. But it is interesting that it's a little more massive than the sun, which means this is the kind of red giant that the sun will turn into in 5 billion years. This is not one that will go supernova. Betelgeuse is more massive. That one will blow up. Aldebaran eventually will leave a white dwarf behind with a planetary nebula. It's similar to what the sun will be.
That makes me wonder if that planetary nebula won't be naked eye visible like the Orion Nebula is, given how close it is.
Yeah, that's fairly nearby.
Dang it. I would love to see that, to test that, I jokingly often tell people, I want to see these things, so I'm going to live forever if that's the last thing I do. So these are some interesting things about the winter sky. I'll go back to that slide one more time. You also, from this image, this is this was taken using a what we call a planetarium software package.
This was Stellarium.
Stellarium. Yep.
So you can download this for free. In fact, if you want to find where things are in the sky, go to stellarium.org, O-R-G, and you can download this. It runs on Mac, Windows, Linux. I use it in the planetarium for planetarium shows. And there are a couple planets out. And so this is tonight. So if you go out tonight, look in the west, you'll see Venus, and then above Orion is Mars. And so you can see those two planets.
I will also point out that in the left center, right above the club that Orion is holding up, you can see the feet of Gemini. So Orion is facing with his shield. The constellation Aldebaran is Taurus. And then Mars is between it and Gemini. And I don't see any of the other zodiacal or commonly known. I mean, most people know Sirius because it's in...
Yeah, we've got Canis Major.
In Canis Major, the big dog. So that's one of the reasons it's called the dog star. And then up above it is Procyon, which is in the brightest star in Canis Minor, the little dog. So Orion, the hunter, has his two dogs with him, facing off against the bull, with Gemini on his shoulders. And I always point things like that out to people. So, if you can find Orion, you can find a lot of objects.
You can work your way out. Yeah, and I kind of zoomed in on Orion here, but to the right of Mars is Auriga. That's another one up there.
Right.
So, notice Rigel notice how much further away Rigel is than Betelgeuse. It's actually brighter
Than
than
Betelgeuse.
Betelgeuse. It is smaller than Betelgeuse.
Yep.
So
But
why
it's
is
a lot hotter.
right? It's the temperature, and the relationship with brightness and temperature. Blue stars, the hotter stars, are more luminous. They're brighter. So if you have two stars that are the same size, the blue one will be brighter than the red one.
Than the red one, right. So blue is brighter as well as hotter. Red is cooler, but can be brighter
If it's
because
really
it's
big.
larger. Our distance to these objects will make a difference. So like Sirius is actually both massive, so it's hot and blue, but it's also close, relatively speaking. So that's why it's nice and bright. And you can tell a lot just by asking questions and looking at these things. So, anything else we want to look at in this night sky? Anything else? Any other important things that you can point out?
I think we covered everything I wanted to cover.
Yeah, I mean, there's a few other objects in Orion and everything, but I will leave that to you to determine what those are, and to work out some of the joys of looking up at the night sky. And I do recommend, go look at Stellarium or one of these planetarium software. There's several for your phone as apps. They're varying, very varying quality and reliability, though. So do keep that in mind. And after that, is there anything else you wanted to add, say, or get into? I'm guessing not.
Covered what I wanted to cover.
All right.
So do we want to move on to?
So the question is do we want to move on to what I set up? Because I wanted to talk about how do we know technique, and to be honest, we'll dive right into it because we've kind of brushed up against it. How do we know there are other planets around stars? And I mentioned a couple episodes back various techniques and everything. So I'm going to get into the real powerhouses because I mentioned radial velocity. So what is radial velocity? Well, radial velocity, once again, uses the Doppler shift of the fact that if a source of waves, like light, is moving, then it will change the wavelength of the light. So if I'm looking at, say, the hydrogen alpha line that we mentioned, this nice red line that we know hydrogen gives off, and I see it a little redder than it should be, and yes, I can identify that line, whatever its color, because of the spacing of lines, then I know that source of that hydrogen alpha line is moving away from me. If it's a little bluer than it should be, then I know it's moving towards me. Well, just as the gravity of a star keeps a planet in orbit around it, so too does the gravity of the planet tug on the star a little bit. So the planet, we always like to say that the Earth is in orbit around the sun, because pretty much it is. But in reality, the sun is in orbit around the center of mass of the Earth-Sun system. It's just that center of mass is very close to the center of the sun, because the relative mass difference is huge.
Yeah, the sun is like 99% the mass of the solar system.
Pretty close, yeah. So Earth does not produce a big wobble, but a planet like Jupiter will actually produce a noticeable wobble, a noticeable back and forth swing of the star as it orbits that center of mass between a Jupiter-sized planet and its star. And so we're able to take that. Dang it, I had another slide I wanted to put in there and I messed it up. Oh well. We're able to take this difference that allows us, we're able to measure that difference in the wavelength. And from that, we're able to determine how fast the star is moving away from us or towards us. And we get this nice velocity curve. Now, this is for 51 Pegasi, and it does have an exoplanet, and it's a fairly massive exoplanet that's in pretty close to the star. How do I know that? Well, this capital P tells me that its period is 4.231 days. Okay, so this planet, Mercury, for instance, goes around the sun 88 days.
I think so, yeah.
Yeah. We don't keep a lot of this stuff in memory, folks. We've got books for that, or the interwebs. So Mercury takes 88 days to go around the sun. This planet takes 4.231 days. It is plural. So this is much closer to its star than Mercury is. It produces a wobble in the star of 56.04 meters per second. And so we see that nice wobble as this nice sinusoidal curve as the star wobbles back and forth towards us and away from us as it goes around that star. And Wayne is fairly tuned in with us and asking if we're having fun yet. And we are having a blast. Despite a major mess up on my part at the beginning of the show, we are having a blast here, folks, right? Right. So this is what we mean when we're talking about radial velocity measurement. And this is one of the two big workhorses. This is the method that has found the most, if I'm not mistaken, exoplanets of any of the other methods. Most of them have been found by radial velocity methodologies. Okay? The other big workhorse is transit. And basically what this is we measure the brightness of the star, and if something goes between us and the star, like a planet, the star dims a little bit. All right? And that dimming, how much it dims, depends on the size of the planet, the size of the star, and things like that. And so you get these relatively different shaped dips in the brightness, the dips in the brightness curve. And so here we have 5 different stars with their exoplanets that go between us and the star. And as you can see, they have a nice bottom to them. Well, how do we know that's a planet, not just another star? Because stars go in between each other as well. Well, I did this nice light curve of a star called AZ Virginis. It's in the constellation of Virgo. And as you can see, this is 2 stars. Well, if you notice, going back to these others, all of these light curves, they have a broad bottom. It may be curved, but there's a definite breadth to the bottom of the light curve of where that dip happens. Well, if we go back here to the 2 stars, there is no breadth to that bottom. It's pretty much a V shape. So that's how we know it. It comes about because stars are roughly the same size as each other. Okay? If they're on the main sequence. Caveat. If they're on the main sequence, they're roughly the same size. The size of the star does not vary a whole lot on the main sequence with the mass of the star. Oddly enough, and there is a reason for that, but I invite you to take an astrophysics course because that would take longer than an hour to explain. So anyway, you've got that dip for the binary star. So we can find planets if they are aligned. Everything is aligned so that their orbit brings them in between us and their star. And we can see them, and I've got several different measured light curves like this myself. So this is the other main workhorse. This is how we determine, yes, there are planets around other stars. The star dims, and it dims with a certain pattern to it that can't be the fact that there's another star or something there. So the next method I want to discuss and look at is called astrometry, which all astrometry means is measuring the position of the star. So we can take very precise measurements of where a star is on the sky. And as I mentioned, if the planet is there, it's tugging on the star, just like the star is pulling it into orbit. So they're kind of in a mutual orbit. And what this will do is as in the lower section of the lower box of this, is it'll make that star make this little curlicue pattern as it moves across the sky. Now, this curlicue set of curlicue patterns like this, if the star had no planet, it should just move in a straight line across the sky. So it's being pulled out of that straight line. And this data is taken over the course of many, many years. And that's the limit and why there's not more planets found with this method, is the star has to be fairly close for us to use it. We're just, these motions are extremely tiny. I mean, it takes on the order of hundreds, if not thousands of years for the constellations to change shape, right?
Yeah, so you don't notice.
So you don't notice that, you won't go out and see this movement with your naked eye by any means. But with very, very careful measurements of where things are through a space telescope, we are now able to see this drag, this wobble produced by a planet directly. So that's kind of neat.
I would guess this has to be a space telescope. I think the atmosphere
Absolutely.
fuzz this up.
Because this is on the units for this are micro arc seconds. Now, what an arc second is, a micro is a millionth, 1/1,000,000. And an arc second is 1/3600th of a degree. So take a degree, which is about the thickness of your index finger, I think it is, held at arm's length.
I always think the full moon is half a degree.
Okay, the full moon is half a degree. That's a good way of thinking of it. So that's half a degree. Yeah. Do 1/3600th of that, and then do 1/1,000,000th of that. That's how little this movement is. So, this is not big major movements. It requires a telescope in space because the atmospheric wobble produced by the shimmer, the thing that makes stars twinkle to us, is a bigger effect than what this movement is.
So this is not a common method to find exoplanets.
This is not a common method.
Radial velocity and
radial
transit.
velocity and transit are the workhorses. Those are the main ways.
And we had, the Kepler spacecraft just sat and stared at a patch of the sky looking for transits. And found a lot of exoplanets.
Yes, it did.
That way.
And had a lot of ground confirmations from what it found. So that's it. So there's one other that I'm really going to discuss, and that's pulsar timing, which was the first method ever used that detected a planet, and it was discounted at the time. Now, a pulsar is a type, Betelgeuse will produce either a black hole or a pulsar. It takes a massive star that explodes in a supernova to produce a pulsar, which is a type of neutron star. So these are rare to begin with, and there was nobody expecting planets around them. But how does this method work? Well, a pulsar normally has a beam that, if it intersects us, we detect it as a pulse of radio, or, as we found with one pulsar, visible light.
So it's a rotating beam. People
So
will
it's
talk
a rotating
about it
beam.
like a lighthouse.
Like a lighthouse. And so it's a very regular pulse, as shown in this graph. This is the pulse inside the Crab Nebula, which is a supernova remnant found inside of the constellation Taurus. So you can see it's a very regular pulse that sweeps across. Well, if there's a planet around that pulsar, that lighthouse, it's like the lighthouse is wobbling. So sometimes the beam intersects you fully, and sometimes it doesn't quite intersect you fully. And so what you get is this regular set of pulses, but they vary in intensity. And so this was the first actual exoplanet that was detected, was around a pulsar using this method. And everybody assumed that there couldn't be planets around this, so it was actually swept under the rug for many years until they detected a planet via radial velocity method and said, hey, we are finding planets now. Well, wait a minute, wasn't there something about a planet around a pulsar? They went back and had one of those times when we as scientists had to go, oh, oops, sorry. And credit back in 1990 that they had discovered, or 1991, that they had actually discovered the first exoplanet orbiting a pulsar, of all things. So these are the main methods. There is another method called gravity microlensing, which uses the gravitational lensing effect that we've talked about many times, but that's even less useful than astrometry or pulsar timing. So that's our topics for today. I'm assuming there are no questions because there hasn't really been any chat. And I know I threw a lot of at you real hurriedly. So if there are any comments or questions, by all means, throw them at me in the comment section of this video when we get it posted. And we'll do our best to answer. So on that note, I will make a final plug for the university. If you are interested in the sciences, especially physics or astrophysics, I encourage you to look at the University of North Dakota, and in particular, the College of Arts and Sciences and the Department of Physics and Astrophysics. We have joked about the weather, but it's not like you go stand out in it, so don't be afraid of that. And come join us. Come look at us. If you have any questions about that, feel free to contact us. So that's that. And like usual, we will end with a quote, which this one is from Steven Weinberg. The effort to understand the universe is one of the very few things that lifts human life a little above the level of farce and gives it some of the grace of tragedy. So go out there and find things out or ask people who can help you. So y'all have a great week. We'll see you next week. Let's see, what will it be? March 28th. We will get it live this time at 3. And yeah, sorry about that. But anyway, y'all have a great time. Dean, any closing thoughts or words?
Hopefully you have some clear skies and you can go out and enjoy the spring weather, the beautiful spring weather that we have right now.
All right. Good night. Good afternoon, everyone. Y'all have a great day.